Hello, my name is Cristina Zavaleta, and I'm an assistant professor in the Department of Biomedical Engineering at the University of Southern California. Before joining USC in 2017, I was at Stanford University, where I trained in the molecular imaging program under the guidance of Dr. Sam Gambier. I had the privilege of becoming one of the inaugural members of the Michelson Center for Convergent Biosciences at USC, where we have faculty from different disciplines coming together to promote human health. My research team focuses on developing new molecular imaging strategies that utilize nano-based imaging contrast agents. Now, we believe that nanoparticles actually have several advantages over their small molecule counterparts to actually help improve patient outcome. We want to provide physicians with new molecular imaging tools to help identify that molecular expression of a particular disease process. And one of the projects I'm excited to share with you today uses a nanoparticle made of gold and silica that we call a surface-enhanced Raman scattering nanoparticle. These nanoparticles inelastically scatter light differently depending on what molecules we absorb to the gold in the Raman active layer, shown in red here. I was fortunate enough to help pioneer this new molecular imaging strategy that uses these unique nanoparticles. And what's really neat about these nanoparticles is that we can actually switch out the molecular layers, that Raman active layer, with a different molecule that will inelastically scatter the light differently and thus produce very unique spectral signatures that you could think of as barcodes. Now, get ready for something truly spectacular. We've been able to actually expand our Sears library to 26 unique flavors. So unique Raman nanoparticles with their spectral signatures. So you can imagine how powerful this tool could be for interrogating multiple events simultaneously. If each of these nanoparticles has its own unique barcode associated with it, then we can actively direct each of them to interrogate something different in a single image simultaneously. And what we've successfully demonstrated is the ability to detect and unmix all 26 of these nanoparticles in a single imaging pixel when combined together. This has never been done before. Nanoparticles have never been able to be unmixed to this degree, and it's a huge step forward for the field of spatial molecular profiling. With the advent of personalized medicine, there's a significant need for molecular mapping across a patient's tissue to improve drug discovery and enable precision medicine. However, the current gold standard uses a chromogen-based immunohistochemistry assay and is typically limited to the interrogation of just a single biomarker on a given slide. Our strategy would involve chemically conjugating separate batches of our nanoparticles with antibodies specific towards a given biomarker and administering them together to a histology slide. The resulting image would be spectrally deconvolved to reveal separate channels that represent the expression of multiple biomarkers simultaneously across the single slide. We were excited to see that when our nanoparticles are conjugated with specific antibodies, they actually have great targeting capabilities in cell culture to multiple types of biomarkers overexpressed on specific cancer cell lines. Now, these cell lines were mixed with our targeted nanoparticles, and you can see a nice correlation between the Sears Raman imaging channels and the white light microscopy images that show the cells. And finally, we were thrilled to see that our conjugated nanoparticles can actively target HER2 on formalin-fixed paraffin-embedded human tissue sections. This was a histology slide from a patient with ductal carcinoma in situ with an overexpression of HER2, and you can see that our Raman image matches nicely with the gold standard IHC chromogen stain, revealing a very similar pattern of expression of HER2 across that tissue. We believe these preliminary results have significant implications for the development of an entirely new molecular imaging technique that's going to offer unprecedented multiplexing capabilities to characterize that spatial protein expression across the tissue. We're continuing to evaluate the expression of multiple targets and are excited to further develop this new multiplexed imaging platform. We really believe that this new molecular imaging strategy has great commercialization potential, as the field of proteomics is a $25 billion industry that's expected to have impacts across several areas of biomedicine, including drug discovery and personalized medicine. We're looking to spin out this technology in the next couple of years, so we're excited to get to know any potential investors, as well as to develop partnerships and collaborations with academic or industry groups to further support the commercialization of our innovative Raman proteomic imaging platform. Please feel free to email me if you have further questions or are interested in collaborating, and thank you for your time.